Okay, good afternoon everybody and welcome to Alarm Corp's final CCTV webinar for 2011. My name is Piotr Tolecki. I am the National Product Manager for Alarm Corp for CCTV, and today's webinar is on megapixel cameras, mega performance or mega myth, an objective look at some of the pros and cons of megapixel cameras. First of all, a little bit of housekeeping. Some of you may have used GoToMeeting before, some of you may have not, so for the benefit of those who haven't, let's just go through the features of GoToMeeting fairly quickly. You will see on the GoToMeeting toolbar on the right of your screen the following. There is a microphone icon which will be crossed out. You will be muted for the duration of the presentation. Next, there is a raise hands icon. Now that allows you to raise hands to grab my attention. Now just to verify that you can all hear me and that you can all see my screen, can you all please click on the raise hand button? Okay, great. I'm starting to see a few hands going up. Thank you. If you can put your hands down, that will be great. Okay, next. Questions. We will go through any questions you may have at the end of the webinar. Please feel free to type in your questions at any time during the webinar. You don't have to wait till the end. I will simply go through them in the order that they are received. Once you have typed in your question, make sure you click the send button to send me the question. Okay, with the housekeeping out of the way, let's begin. Today's agenda will cover the following. What is a megapixel camera? Some common resolutions, the advantages of megapixel cameras, the weaknesses of megapixel cameras, applications and some design issues to consider, and finally some conclusions. So we have a fair bit of information to go through today, but I hope you will find it informative. First of all, what is a megapixel camera? All video cameras have image sensors made up of pixels. Now in this sense, it doesn't matter whether we are talking about a CCD camera or a CMOS camera. Traditional cameras have approximately 780 by 580 pixels. So the total pixel count is approximately 440,000, which can also be expressed as a 0.4 megapixel camera. And the maximum resolution of these cameras is limited to around 540 TV lines. And this is when you take into account the effect of both the camera and the lens and, of course, the transmission of the signal. So what is megapixel? Megapixel cameras are cameras with more than a million pixels. The higher the resolution we want, the more pixels we need. So in essence, all megapixel cameras have 1 million or more pixels. It does not necessarily mean that the pixels themselves are larger, and this is something that we will discuss shortly. Okay, some common megapixel resolutions. 1.3 megapixel, which equates to around 1280 by 960 pixels. 2 megapixels, which is approximately 1600 by 1200. 3 megapixels, which is approximately 2000 pixels by 1500. And 5 megapixels, which is around 2400 by 1600 pixels. Now, the megapixel myth. What is the megapixel myth? There is a bit of a perception out there that more pixels always equals better quality. And this is largely driven by the consumer products market, especially digital video cameras. If you look at the successive releases from either Canon or Nikon or any of the majors, each successive model has got more pixels than the previous one. Today, most digital cameras have approximately 12 to 14 megapixels. You know, only 12 months ago, 7 to 10 megapixels was quite common. Yet, when we come to video surveillance, CCTV cameras are still stuck at single digits. Why is that? So let's explore that a little bit further. Now, the benefits of megapixel cameras are fairly clear. Higher resolution is the first one. More pixels mean we can have more details, which gives us potentially sharper images. And especially on playback, we can zoom in without blockiness, without the same degree of blockiness that we do with existing classical resolution cameras. And if you look at here, let's say this is a portion of an image taken at standard resolution, which is 704 by 576. Next, if we increase the pixel count, you can see that we can get more details and less blockiness. If we increase the pixel count again, the image becomes sharper again. So by the time we get to 6.5 megapixel resolution, which is approximately in this example, we can zoom in a lot closer. Now let's compare that to some classical resolutions. SIF in the first instance, which is 328 by 288 pixels. So it's 320 by 288. Now this is a SIF image actual size. If we were to blow this image up to its full screen, you will see that it becomes quite blocky. We can see where the roof of the yellow car is joining. We see a lot of blockiness, and we definitely cannot make out any details. Next, if we go to full SIF, which is 704 by 576, and this is the classical PAL resolution that's been used for years, we can see straight away that there is more detail in the image. The curved lines and the bent lines are not as jagged. Yet, however, we still cannot read the license plates with any confidence. And we can sort of guess as to what the models of car is, but we can't really read the badges. So if we jump from 4SIF up to 720p, you can see straight away, we can now make out clearly that the car on the right is a Ford. We can see that it's a Belgian number plate. We can read the number plate, and we can see, for example, that the car on the left is a Volkswagen. We can read the license plate, and we can even make out the fluffy white rabbit or gray rabbit on the back parcel shelf. So this illustrates the principle that as you have more pixels, the image becomes sharper. So the benefits are clear. If we stick to the same classical measure of so many pixels per foot or per meter resolution, we can cover an equivalent area that we would need for classical cameras with a single megapixel camera. We will end up with the same resolution as before. However, we only need the one camera. However, megapixel cameras are not without their disadvantages. First of all, lower sensitivity, higher bandwidth and storage requirements. There are specific lens requirements and also some installation requirements. And we will discuss these in more detail in the following slides. First of all, let's look at sensitivity. For a given sensor size, as in 1/3, 1/2, 1/4, the more pixels we pack into that sensor, the smaller each pixel must be. Therefore, each pixel can capture less light in a given time. And this is equivalent to if you were trying to capture rain. If you've got a bigger bucket, you will capture more raindrops than you will if you've got a smaller bucket. If we were to keep the pixel size constant, the sensor size would have to increase together with the pixel count as shown in this example. Now, of course, it is possible to do that. And those of you who are familiar with digital SLR cameras will note that a 12 megapixel digital SLR has a pixel that's about 4 or 5 times the size of the pixel inside a little compact. However, if we have a bigger sensor, we have to have bigger lenses which have more glass. So this automatically makes the lens more expensive to manufacture. And again, if you've ever tried to buy a lens for a digital SLR, you'll know what I mean. If the camera is bigger, if the lens is bigger, we need a bigger housing. And this automatically adds to total system cost. And of course, the bigger the camera, the heavier the camera becomes. It means our housing and our bracket must also be more robust. So for that reason, most megapixel sensors end up keeping the same size, which means that the pixels become smaller. So let's look at that in a bit more detail. In a classical standard definition camera, if we look at a portion of the sensor, we see that in this example we are looking at 4 pixels. The sensitivity is 0.1 lux, which means we only need one, in this example, one candle to illuminate the sensor to get enough light to get an image. If we go up to 1.6 megapixel camera in this example, we have exactly 4 times the number of pixels in the same unit area. Therefore, each pixel is a quarter of the size. So now, if all other things are equal, that pixel will need 4 times the amount of light to achieve the same signal. Or in other words, the sensitivity is 4 times less sensitive. If we increase the pixel count again, and we go up to 6.5 megapixels, we now have 16 times as many pixels in the same unit area as we did before. It means that we now need 16 times the amount of light as we did at the classical resolution to generate the same response from our pixel. So straight away you can see that as the pixel count increases, as the pixels become smaller, each pixel needs more light. So now what can we do to improve megapixel camera sensitivity? Use the biggest sensor we can get away with. In megapixel cameras, we have a choice often of 1/3 image sensors or a 1/4-inch image sensors. A 1/3 image sensor will typically always be more sensitive than a 1/4-inch sensor. We can use longer exposure times. However, this can have problems for applications. The longer the exposure time, the more smear or ghosting we can have. And in this example, where we're trying to capture a moving car, you can see that the number plate is completely smeared. So using longer exposure times would not be a good idea if we are looking at capturing moving traffic. Next, we can use more gain, in other words, increase the automatic gain control within the camera. However, electronics being what it is, this will add more noise, as in this example. And when we add too much noise, we can actually end up going backwards with the image becoming grainier and more noisy, which then will counteract the inherent advantage of having smaller pixels. Now let's put some numbers around this. A classical resolution camera, such as Intellogic's UltraView 4SIF H.264 camera, we can see that its resolution in color is 0.05 lux at f1.2. Next, we look at a TrueVision 1/3-inch HD 720p camera, which has got 1.3 megapixel resolution. Note here, the sensitivity in color is now 0.1 of a lux. So just in going from 4SIF to 1.3 megapixel, we've effectively halved the resolution. And you can see that both of these figures are done at exactly the same f-stop. So they are a direct comparison. Next, we go up to a 2 megapixel or full HD 1080p camera, which is also a 1/3 inch, but in this case it's a progressive scan CMOS sensor. And note here, we now have a sensitivity of 0.68 of a lux. So you can see that the 2 megapixel camera is 1/6 as sensitive, or 6 times less sensitive than the 1.3 megapixel camera. And these are real figures taken off actual camera data sheets. Next, we look at the bandwidth requirements. The more pixels we have, the more data there is to encode and transmit, which has a higher network load. Therefore, we will need more storage space to record the same number of days. So the key takeaway of this slide is that resolution comes at a cost. Now you see here in this graphical example, when we move from 4SIF to 1.3 megapixels to 6.5 megapixels, roughly how much more storage we need in the expressed as the number of hard drives. Now this is shown for MJPEG compression. H.264 is comparable, even though the bandwidth requirements of H.264 itself are significantly lower than MJPEG. When we compare H.264 at standard resolution versus H.264 at 1.3 megapixel, the multiplication factor still holds. So, if we look at a 4SIF camera, H.264, 25 images per second, we have approximately 1.5 megabits. And this is for real time. If we take a TrueVision 1.3 megapixel camera at 720p, at 12 images per second, which is half real time, you can see we're just under 1.8 megabits per second, or 1792 kilobits per second. If we now ramp this camera up to 30 images per second, at the same quality settings, we are up at 6 megabits per second. If we take a TrueVision 2 megapixel camera at XGA, which is 1280 by 1024 resolution, you see that at 12 images per second, we are running at just over 4 megabits per second. If we now take the same camera and run it at 30 images per second, we're up to 8 megabits per second. And these figures are actually taken from the recording calculator, so they are real numbers. So straight away, this tells you that if you want to stream these cameras at this resolution, these are the bandwidths that we need to plan for. To put it into perspective, we could have 6 standard resolution cameras taking up roughly the same bandwidth as a single 2 megapixel resolution camera. So again, this just highlights the fact that higher resolution comes at an added cost, and in this instance, we have a higher network load, and conversely, if we choose to record this data at these bandwidths, we will need more storage space to give us the same number of recording days. So we need to consider these bit rates when designing a system. Can the network switches handle the traffic reliably? What will be the impact of this video traffic on other network users? And this is particularly important if we're looking at putting on megapixel cameras onto an existing system or an existing network. Say it's a legacy system where we've had a normal camera that was running at VGA and we want to upgrade it to 1.3 megapixels or more. Storage size and storage cost. Typically a lot of the jobs that I see coming through now are asking for 30-day storage or more. The cost of 30-day storage for 4-SIF cameras versus the cost of 30-day storage for 2 megapixels, we are looking at 4 or 5 times the storage capacity. So that will impact the cost, not just of the storage themselves, but also rack space. We need more hard drives, we need more server space. This in turn generates more heat, which will then impact on the cooling cost, how much air conditioning we need to keep this server bay cool. And finally, impact on NVR performance. There are many NVRs on the market, and many can claim real-time at 4-SIF resolution for 16 channels or more. However, some of these NVRs will show that they need to be throttled back when going into megapixel. We have to either throttle back the frame rate, or we have to reduce the total number of camera channels being used on the NVR. And if we think about it, that should not come as a surprise. At the end of the day, every NVR has got a certain bus inside it that can pump so many kilobits or megabits per second through the bus onto the hard drives. If we exceed that maximum throughput, then something has to give. We will either bottleneck the system and crash the NVR, or there will be packets and frames being lost. So that's a question that you need to check for the NVR that you're choosing to use in your application. Can it handle the same number of megapixel cameras as it can with normal cameras? Okay, next, we look at CPU load. If you choose to view megapixel cameras on a workstation, this will require more CPU power than viewing a standard definition camera. This may mean we need a higher specification PC, which means higher system cost. And this has to be considered when designing a system, or poor performance will result. Now, we know that we are dealing in a market where our customers will always use the latest PC. None of you have ever come across an installation where a customer has had a PC that's 5 or 4 or more years old, still running Windows 2000 or even Windows NT. If only that was the case. So let's look at some concrete examples. We see here CPU requirements for TrueVision Navigator. And you'll see that a minimum spec will do with an Intel Pentium G6 950. Conversely, a high spec requires an Intel i7. Now, if we're looking at a small system with only a handful of classical resolution cameras being viewed at SIF, then the minimum specification will be more than adequate. However, if we do go onto a system where we want to view megapixel cameras and several megapixel cameras simultaneously, then we will need to use the high specification CPU. And of course, there will be a cost difference between the two. To give you another example, this is an actual screen grab of a PC that was running TrueVision Navigator. And you can see the CPU usage history, which was newly peaking at just under 90%. And then it dropped suddenly. I captured this curve when I was running some megapixel camera tests and then switched the megapixel cameras off. So you can see straight away the difference a megapixel camera makes to the CPU load. And that was actually a reasonably high-spec PC. It would have probably fitted into somewhere in the recommended, around the i5 level. So again, this gives you an illustration of just the impact on CPU load that viewing megapixel cameras can make. Now we've looked at the network bandwidth. We've looked at the CPU load on our video management station. Now let's look at lenses. When we are dealing with megapixel cameras, we must match the lens and camera resolution. For example, if we choose to use a 1.3 megapixel camera, we can put a 3 megapixel lens on it. However, we should not put a 1.3 megapixel rated lens on a 3 megapixel camera. Likewise, focusing and depth of field become much more critical with megapixel cameras, otherwise we lose the benefit. Now we've all known that f-stop has a big bearing on the depth of field. Obviously, the bigger the f-stop, the bigger the depth of field. However, the bigger the f-stop means we have less light reaching the sensor. And coupled with the inherently lower sensitivity of megapixel cameras, again, this limits how much we can stop the f-stop down to give us the depth of field. And you can see in this illustration, objects outside the depth of field are going to be unsharp. Now, once they're unsharp, it really doesn't matter whether we're dealing with a megapixel camera or a normal resolution camera. We are still dealing with an unsharp object. So this highlights the fact that if we are using a megapixel camera for an application, we have to be really, really conscious when commissioning the camera as to where is the optimum depth of field in our field of view, to make sure that if we are using the megapixel camera, that where we are trying to capture the objects of interest, those objects of interest are at the point where the sharpness is maximum and not outside the depth of field. And this gives us an example of what happens if we use a normal lens on a megapixel camera. You can see in the left example, the image is quite sharp, whereas in the right example, we've put a normal resolution lens onto a megapixel camera. And this again should come as no surprise. If you Google some of the articles by Les Simmons, who has done a number of tests on various lenses, you'll see that most classical lenses are limited to around 500 or so lines of resolution, which is adequate for normal resolution cameras, but is really not good enough if we are looking at 720p or HD 1080p type resolutions. So lenses become much more critical with a megapixel camera. Now, some of the applications for megapixel cameras are already well known. They are particularly useful in retail. You know, if we look at it in this shop, we can see much more closely the types of products that our customers are looking at. Likewise, we should be able to capture more easily the details if somebody is trying to shoplift. If we look at sports venues, airports, education, it becomes a lot easier because of the added detail to make out passengers, the details of their luggage if somebody is acting suspiciously. Likewise, in car parks, traffic surveillance. We've already seen that with the inherently high resolution, number plate recognition, even without specialized software, but just recording the number plate details on a normal NVR becomes a lot easier. Having said that, we need to keep in mind what we said earlier about the sensitivity if we have moving cars. However, if we are looking at a car park, it is not beyond difficulty to put up a megapixel camera on the car park entrance or exit where we know that the car has to stop and wait for the boom rate to go up. So these are probably the most common applications where megapixel cameras can be used with a lot of success. Now, what are some of the alternatives to megapixel cameras? We know that megapixel cameras have got some issues that need to be considered. So sometimes they are not the best choice, and it does depend on the application. We can use a single standard definition camera in lieu of a megapixel camera. Now, first of all, this is likely to be less expensive, both in terms of the camera itself and of the storage requirements. It will almost certainly offer much higher low-light performance. However, if we do use a standard resolution camera, we will not deliver the same image quality in good light as an MPX camera would, and our ability to zoom in on playback is going to be limited before the image gets too blocky. However, we do need to ask the question, does our chosen application really need megapixel resolution, or is standard definition sufficient? We can use multiple standard definition cameras in lieu of a single megapixel camera. And I know this sounds contrary to what I said earlier, that we can replace multiple standard definition cameras with a single megapixel. However, if we use multiple standard definition cameras, we have higher system redundancy. We now have 2, 3, 4 cameras instead of one. So with any one camera failure, we still have other cameras surveilling the viewage area. This is still likely to give us better low-light performance. Now, the overall image quality for the whole coverage area can be comparable. Again, when we use the measure of pixels per meter, we can get comparable image quality. We can have multiple viewing angles which we can adjust individually. If we do choose to use a single megapixel camera, then we can only adjust that one camera's field of view. And remember what I said earlier about depth of field. If we are looking at a surveillance area where we have multiple objects of interest and they're all at different distances from the lens, because of the depth of field issue, in this application, we really might be better off using multiple cameras rather than one megapixel camera because of this depth of field issue. However, multiple SD cameras mean overall system cost can be higher, both in terms of equipment and installation. And of course, in terms of maintenance, there are more cameras to clean and maintain. So depending on viewing angles needed, this may or may not be the better option. Now let's look at some of the design considerations when planning to deploy megapixel cameras. If we look at existing sites, is the lighting sufficient? And you know the story, lights have been installed, especially if we're looking at fluoro tubes or halogen lights. Their performance decreases over time. It's one reason why offices need to be retubed every couple of years. And the fact is, standard resolution FOSIF cameras today, most of them are so good that they have so much reserve performance in terms of low light sensitivity that you do not notice the degradation as the lights become less powerful. However, you put a megapixel camera onto that same site and suddenly we might find that the performance is not adequate. We might find that the camera needs to crank up its automatic gain control and straight away the image becomes grainy and fuzzy, which robs the benefit of putting the megapixel camera on in the first place. Existing sites, is the network sufficient? You know, if we've had a site where we were running maybe 16 cameras at SIF or VGA resolution and suddenly we want to upgrade 10 of those cameras to run at 720p or 1080p, and we know that the network switch in there might be 3 or 4 years old, will the throughput of that switch be sufficient now for megapixel traffic? It's something that needs to be checked. Likewise with either a hybrid video recorder or a network video recorder. Are there any restrictions when using a megapixel camera? Let's say we look at a TrueVision TVR60, which is a hybrid recorder. Now this can have either 16 analog channels and up to 8 IP channels. But those 8 IP channels are at standard resolution. So if we choose to continue with all 16 analog cameras being used and we suddenly want to replace some of our IP channels with HD 720p cameras, then on the TVR60 we need to either decrease the frame rate or drop the number of cameras. Next, is the proposed megapixel camera the best one for the application? And this is particularly in the context of sensitivity. And also, if we look at, say, a TrueVision 1.3 megapixel camera, it is a true day-night model. It can work with infrared lights when in night mode. If we look at a True Vision 2 megapixel camera, that camera is not compatible with infrared illuminators. So again, we need to go back and check what is being used on site. Do we have IR illuminators? If we want to continue using them, then we need to make sure that the camera we choose is compatible with that. And finally, has the right lens been chosen? Okay, conclusions. Megapixel cameras can be a very powerful CCTV tool. They can provide much higher image quality. They can provide more details than standard definition cameras ever can. But they do have limitations. A higher pixel count is no guarantee of higher quality. In general, the more pixels we have, the lower the sensitivity becomes, so we need more light. Likewise, the higher the pixel count, the higher the bandwidth, the more network load we have, and the more storage we need for a given number of days. Using the right lens is critical, and setting it up is also critical. And finally, megapixel cameras may not be suitable for all applications. Okay, would you like to know more? More information, including brochures and datasheets, may be found on our website, www.alarmcorp.com.au. If you haven't done so, I would urge you to subscribe to the Alarm Corp Pulse newsletter to receive new product information automatically. If you register online with Alarm Corp, you can get full access to our e-commerce platform, including your own customized pricing and order placement. Please feel free to contact your nearest Alarm Corp representative, either Jeff Rushton or Diane Brazil in New South Wales, or Stephen Dinger in Victoria. And the email addresses are given, as are the mobile phone numbers. Also, you can contact myself, Piotr Lecki, direct on my mobile number, 0421-378-334, or email me at prd@alarmcorp.com.au. Now, this was the last scheduled CCTV webinar for 2011. Webinars will restart in February 2012, and details will be available towards the end of January. So please go to our website and click on resources and then follow the webinars link. This will give you a list of the upcoming webinars. And also, this link will allow you to download presentations for past webinars. So if you've missed a past webinar, we record all of our webinars, and those recordings are available for download. So we look forward to your participation. Okay, if you haven't done so, I'd urge you to visit our website now. Our website has been redesigned, information is easier to find than ever before, and keep checking back for regular specials. Okay, that concludes the presentation. Now it's over to question time. So again, please feel free to type any question and hit the send button, and I will go through the questions in the order that they are received. And I will stay online as long as the questions keep coming.